Now, most acids that we deal with are actually weak acids, and so the concentration of the hydronium ion at equilibrium is the most important factor for determining what the pH of these solutions are. And so in order to do that, we typically need to use what's known as an ice table to calculate the concentration of hydronium ion at equilibrium. When we're talking about weak acids by definition ionize to a very small amount in water. So when we have a weak acid, we add it to water, the equilibrium with hydronium ion and then this conjugate base, we know that Ka, when we calculate Ka is very small, meaning that the amount of products divided by the reactant is actually very small. And so the values for Ka are 1 times 10 to the minus 4 all the way down to 1 times 10 to the minus 9. And so this means that a very, very low amount is ionized in water. And so what this means is when we put an acid in solution, a weak acid in solution, the change in the amount of hydronium ion from the initial concentration, which to be honest is practically zero, so of course in our ice tables is I, so this initial concentration is practically zero. The change from this equilibrium concentration, from this initial concentration to equilibrium, is very small because Ka is very small, because we're talking about a weak acid. And so we can use this when we talk about looking at questions. So for example, here's a typical question, and it says, what is the concentration of hydronium ion in a 0.534 molar solution of formic acid? And we're given the value of Ka. And we're given the value of Ka, and we see that the value of Ka, 1.8 times 10 to the minus 4, is very small. And so what we want to do is we want to set up our ice table for this at the beginning. And so formic acid, if we looked at formic acid, this is formic acid here, just has one carbon, would be methanoic acid. This hydrogen here, which is attached to this oxygen, this is the acidic hydrogen that would make the proton that we would take off, as it was a donor of H plus ions. So here in the initial instance, this is the concentration of formic acid that's added to the vessel, 0.534 molar, here it is, and the concentration of hydronium ion at the initial time is 0, or approximately 0. And this is an assumption that we're going to make, which is based on the auto-ionization of water, which you would have read about in your textbook. And I'm going to explain that a little bit more in a second. And then in this case the conjugate base here also has a concentration of 0, because at the initial time point nothing has happened, nothing is ionized. And so the change that occurs when we go to equilibrium we call X, and so the concentration of formic acid decreases by a value of X. And because this is a one-to-one relationship and a one-to-one relationship, the concentration of hydronium ion increases, small amount of course, and the concentration of this conjugate base also increases by a value of X. And so when we get to equilibrium, as part of our ice table, our concentration of formic acid is 0.534 minus X. Our concentration of hydronium ion is plus X. Our concentration of the conjugate base is plus X. And so now we can write an expression for Ka. So Ka, remember, is the products divided by the reactants. Of course, if there's any power associated with the stoichiometry of this equation, which are all 1. And so now we can plug in these values, X, 0.534 minus X, which is the concentration, always at equilibrium. And so at this point we can make some assumptions. And so the first assumption that we can make is that at the beginning, in the initial solution that we have, we can say that the concentration of hydronium ion that comes from the auto-ionization of water, because as soon as we have water available in our vessel, there's a very small component, 1 times 10 to the minus 4 from a kW point of view, that actually dissociates and produces hydronium ion. And the assumption that we can make is that the amount of this autoionization that is occurring is very small, so that at the initial value of hydronium ion, this is going to be approximately 0. And we need to make that assumption, and we need to make it clearly. And the second assumption that we can make is, as Ka is small, because it's a weak acid, and that the concentration, the initial concentration is large, so 0.5 molar is a large concentration, and we can assume that the equilibrium concentration of formic acid, which started at 0.534 molar, minus this value of X, which we know is going to be pretty small because it's a weak acid, and we also know that the Ka value that we're given is a small value, tells us it's a weak acid. We can make this assumption that because this value of X is going to be very small in comparison to this, we can make the assumption that this value is approximately equal to 0.534, because this value is very, very small. And so of course we're going to test this later, and the way we can test this later is we can determine what this value of X is. We can determine how much of a percent of this value X was, and if X is less than 5% of the initial value, then this assumption is valid. And between you and me, for most weak acids that start in relatively concentrated amounts, this is indeed a valid assumption. So now if we go all the way back here, we get back to our Ka expression, which is X times X over 0.534 minus X, and we're going to use the assumption, and our assumption is basically saying that this value here is equivalent to 0.534, because this value of X is very small. And so here in this expression, this value of X minus X has been removed by using this assumption, and then we can go through and we can rearrange this equation so that if we multiply both sides by 0.534, X squared equals 1.8 times 10 to the minus 4 times 0.534 molar. This gives us a value of X of 9.8 times 10 to the minus 3 molar, which is the concentration of hydronium ion at equilibrium. And so this is the answer that we were looking for. It's to 2 significant figures, so that's all good. Now it would be good to check this assumption, because this assumption that we used up here would be important to check. So we can check this assumption by taking the value of X, dividing it by the initial concentration of the acid, which was 0.534, multiplying it by 100, and we end up with a value of 1.8%, which is significantly less than 5%. So it's a valid assumption that we could have made. And why do we make this assumption? Well, we make this assumption so that this expression here is easier to deal with, and as long as it's a valid assumption, we can use that. And most of the time, as I said, for weak acids, that assumption is going to be valid. And so you know, we could get asked a separate question as well. Well, what's the pH of this solution, of this formic acid solution? And in order to do that, we would need to know the hydronium ion concentration at equilibrium. So using the ice table as we did before, this was the value of hydronium ion, and we know that pH is minus log to the base 10 of hydronium ion. We put these values in and we end up with a value of pH of 2.0, again to 2 significant figures. So it's a very acidic solution, pH 2, even though it's a weak acid. And so that's the way that we go about using ice tables with a weak acid. And it's important to realize that there are these 2 assumptions that we make. The first assumption being the autoionization of water produces a very small amount of hydronium ion at the beginning, and we can say this is approximately equal to 0. The second one is if K is small, and if it's a weak acid, this is the case. We can say that this initial value, which is large, we can assume that the equilibrium concentration of the acid itself will be equivalent to that at the initial value. And so these are two important assumptions to make when we talk about weak acids.